So I'm Professor Anselmo Frizera-Neto from Federal University of Espirito Santo, and I'm here to present the manuscript high resolution sensors for mass deposition and low frequency vibration based on fiber shift Bragg ratings. Sorry, I have to start the time for myself. Our agenda for the presentation is a brief introduction, followed by the materials and methods, results and discussion. And we are, as this paper was accepted last year, we are presenting what we are doing right now, so we can just discuss something about our current and future directions. And if you have any questions at the end, we can answer. First, this is done as part of the Institute of Applied Computational Science, Intelligence that we're just creating in our state in Brazil. And the idea is to collect researchers that are already interacting with the industry and forming this space for collaboration where we can discuss many applications regarding artificial intelligence, cognition, autonomous mobility, human-robot interaction, and we aim at optimizing industrial operations. In the case of this presentation, the concern was health monitoring of electrical motors. So we are working with an industrial partner that has this laminating for making steel coils for industrial applications. And the idea is to monitor individually each one of these rolls that carry the steel in very high temperature. And at the same time that it's carrying, it's moving back and forward, and it's making like in a very unique and homogeneous format, so they can sell to build automotive applications or any steel applications. They can use this, and it's very hard because what happens, they have more than 200 of these motors driving this steel plate. It's very big, and if one fails, it will leave a mark on the steel, and this steel gets a lower grade, and it's cheaper, or they have to stop the operation, which is also very expensive. So they want to know beforehand if these machines are failing or not, so they can replace the machines before they fail. Right now, what they do is they just go with a visual inspection. So there's a guy with a camera, and he goes there, and every certain time during the day, he has to individually look at every motor and every one of these parts to see if there is some problem there, but he can fail. It's a very harsh environment. The steel comes in red. It's very high temperature, very humid. There's a lot of presence of electromagnetic interference. So making sensors for these applications is quite difficult. And what we are trying to do is using fiber optic sensors because they're intrinsically safe and they have many advantages. One of them is immunity to electromagnetic interference. We have long stability, so we don't have to recalibrate the sensors a lot. And they are usually compatible with harsh environment applications. We already developed these sensors for biomedical applications and for oil and gas industry, and we're just starting this collaboration with this company so we can fabricate sensors for this complex operation. The idea of the paper presented to IEEE Sensors Journal is exploring the use of phase-shift fiber Bragg gratings. And the idea is to have two identical Bragg gratings separated by a phase shift or a defect layer. And what we get is this, let me see if I can get the laser pointer working here. We have this valley, which is very sensitive to mechanical and temperature perturbations, okay? So by monitoring this valley on the reflection spectrum, we can know what's happening to each one of these individual sensors that are engraved into the fiber optics. The idea is, as I said, avoid catastrophic failure, enhance operation safety, and pretty much providing data for the AI guys to study the behavior of these motors and understand what's happening in real time and plan the behavior of the maintenance work, so they can do this in advance of failure. So in this manuscript, we actually explored two main applications. The first one was the mass deposition, which we're not going in a lot of details, but what we did, as this is very sensitive, we deposit very small amounts of salt, and we could show that our sensor is sensitive enough so we can detect the weight of this mass, or not the weight, the mass that was deposited on the fiber optics, so we can study incrustations or any other applications that will require measurement of very small masses. This was one of the advantages of this manuscript. This sensor is very sensitive to, so this peak here, this valley, it moves when we have more mass, so it moves and it's very sensitive, it's easy to measure. But the main application that we are going to present, to the focus of this presentation, is to monitor low frequency vibrations that usually imply in some mechanical failure of some mechanical parts of this motor and reductor component. Okay, so that's what we're going to focus. What we did, we built a device based on a tunable laser, our optical circulator, a PSBG, which is our sensor in these applications. And we, with this optical circulator, what we did, we built a lower cost acquisition device based on a photodetector and a transimpedance amplifier. And with a microcontroller, we could just monitor this valley and see how it's behaving when it's being mechanically perturbated. Okay, so the idea was to make a lower cost application for this kind of sensors, this kind of lower cost sensor for this kind of applications. And the idea is that as we can have sensors in different wavelengths, we can have hundreds of sensors in the same optical fiber, so we can monitor hundreds of motors at the same time. So the idea is to have lower cost sensors, but building in a large amount of sensors, so the guys from the industry can have more and more information about what's happening to each motor. Okay, and then what we did for the manuscript presented in the journal paper was just attaching the sensor to a machine fault simulator. So what's attached right here, and we wanted just to monitor and see if we can get a machine answer. If we accelerate the machine and work in different frequencies of rotation frequencies, we can detect that information. Okay, so that was a quite simple work. And what the phase shift fiber Bragg grating was based on, had this format. Okay, we had this format, which we can see the very small valley here that we are monitoring. And then we use a tunable laser in the same region. So when we have this wavelength shifting, we can just detect the variation of the power, which is easier to cheaper to do than monitoring the whole wavelength and have a complex interrogator. Okay, so what we did is tune the valley to our tunable laser, and then we can just monitor power and see how these answers responds in terms of power, which is lower cost to acquire. And what we did also, we used as a reference a piezoelectric sensor that was already installed in the machine fault simulator that we had. And in this case, we were able to see the frequency response at 4 rotations per second, 6, 8, 10, 12, and 14. And what happened here is that we can show that for many frequencies, we have no error. For many repetitions, so we are just doing over and over, and it's very easy to monitor. For some frequencies, we had quite high relative error in the detection of the frequency. This was related pretty much to the use of the simple microcontroller, and the students that were programming this had some problems with real-time detections for lower frequencies, but this is already solved. And right now, what we can do is just have this very low-cost system to monitor if the frequency of the rotation of the motor corresponds with the vibrations. We also had some problems because of the way this was attached. This was directed, like almost glued to the the mechanical system. So we didn't have any mechanical structure to amplify these vibration settings. But the idea here was to build a very simple solution, easy to implement in the industry, and see if we can monitor the frequency and response of every motors. And if something is failing, this frequency will change, and then we can just use this information for AI detecting the behavior of this motor compound. After this, we kept studying developing our system, and what we did is we looked for in this manuscript an alternative interrogation approach with a tunable laser, just to amplify and to monitor the power oscillations of our sensor in a certain area. But what we want to do now is to enhance the sensitivity of our sensors and use this in a more sophisticated setup with multiple sensors, and we have more let's say, sensitive operations to different conditions of the machines. So if we can monitor if there is a bearing failure, if there is a small sphere inside of a bearing failing, we can monitor many conditions of the motor, including temperature, because the FPGs are also sensitive to temperature. So now we are monitoring frequency and temperature of these systems. And what we did, we attached the sensors to a mechanical structure that amplifies the vibrations. So we made a simulation, and the design simulation manufacturing of these structures, and the optical fiber sensor was placed here. It's not easy to see, but the fiber optic is here. So when this vibrates, this mechanical structure moves very suddenly like this, and then we can amplify these measurements, and the kind of answers that we have is like this, much more complex and much more complete. So we can monitor now up to 1,500 hertz. We can also monitor, if you want, up to 2,500 hertz. And then we can have this frequency signature of the failure that's happening to this motor. As we have this on a machine fault simulator, we can just change parts. So we change a motor which has a certain failure. We can change the bearings. We can change all these attachments. And we can simulate this for getting data for different failures and different conditions. And we just did that. There was a student that finished his master's thesis in this topic. And we have this frequency signature for every failure using our own system. Afterwards, what we are doing now, the future directions, the industrial partner, they provided us with a complete set of this rollator, this roller, motor, and this compound. So we have this in the lab, and now we can install it in a physical, realistic workbench. And what they provide us, they say, look, this motor is failing, and they bring us a motor that they know it's failing. They know the conditions, and we are training our AI and adapting our sensors for practical applications. So this is the immediate future step. Next step, yellow light for me. The next step is preparation of adapting our sensor for work in the harsh environment. So we have to close it and make a good final design of the sensor, but the insides are already done. And then we're going to do a final experimental validation where they are going to let us install 5 to 10 sensors into the process. And then we can monitor this for months and try to predict what's going off these motors based on our previous studies. So thank you very much. This is my presentation. We have 2 minutes for questions.
Thank you very much for the interesting presentation. I have a question regarding your application. So you use an optical sensor due to the harsh conditions, the electromagnetic disturbances. Could you speak about, because I don't have a handle how large these electromagnetic fields get. So is it in a range where electric sensors, let's say traditional force strain sensors, completely fail, or do they just have a large error? So
yeah, what happens here is usually the environment is so harsh and so humid that having anything that's electronic there is not desirable.
Humid?
So, no, electronics. Any electronics, they don't want to have anything electronic close to the application, because it's a lot of water, it's a very high temperature. Of course, there are electronic sensors for that, but in this particular industry partner is very big. They don't monitor this. They just have the process going, and every certain hour, a couple of hours, they go and inspect and see if it's failing. What they wanted is something that could be cheap, and the electronic part of our system could be 1 kilometer, maybe even have close to 5 kilometers from the application, so they can monitor this from an office or for some place. And that's why they wanted us to develop this using optical fiber sensors. The idea, you could use some electronic and have to protect it and calibrate this with the electromagnetic interferences, but usually here the interferences are very high, the motors are very big, and it's not constant because they are operating in different conditions for every lamination process. So that's why we chose for using sensors that are not sensitive to electromagnetic.
Thank you.
Okay, thank you. We have time for one more question.
For the information of this phase-shifted, is it same as the wavelength shifted interrogators?
For the first one, the mass deposition, the individual sensor, we use only electrical, optical power interrogators. But for these ones, which are more complex, we use optical interrogators. So we have a very large wavelength, and we can interrogate the complete complete wavelength. So we can make for every valley and peak, we can have a different sensor. So yes, we use an optical fiber interrogator, commercial one, because it's already validated for harsh environments and for using in practical applications. Thank you very much.